Welcome to EDU World Space.
Okay. In this problem, we have a ray displacement, we have ray diffraction, we have glass with an index of refraction n of thickness t. Should include that in the picture as a thickness t, and we have a ray that passes through the glass. And as in all cases uh, of refraction, when we have parallel surfaces, the incident ray on the left and the outgoing ray on the right should be parallel to each other. And due to the refraction, once the ray emerges, it'll be displaced some distance d from the original beam if it were to pass straight through it. And so we're going to show that if the angle for the incident beam is small, we're going to call this angle theta, the resulting ray displacement will be d equals t theta n minus 1 over n. So to proceed, I've drawn a little picture involving some various angles, mainly this angle theta for the incoming angle, of course, the incident angle. It's also the same angle here relative to the horizontal. It's also the same angle here for the outgoing ray. I've also defined another angle phi, which is this angle here for the refracted light within the glass relative to the horizontal, of course. So to proceed, what we can do is we can apply Snell's law, which is true for all cases of refraction, where we have n air sine of theta equals n glass, or just n, sine phi. Okay, so this is just the application of Snell's law for the situation where for this interface, we're going to call it interface 1. We'll call this one interface 2. Now, for the case where theta is small, we can do some approximations, some small angle approximations for sine and cosine. Remember that when theta is small, it must be the case that sine of phi is approximately phi, and cosine of phi would be approximately 1. So that's very useful. So let's move over to another page to show how this will be useful. So the first thing we can do, we can turn our n air sine theta equals n sine phi. When we apply the small angle approximation, we end up with, let's fill this in a little bit. We'll end up with 1, which is the index fraction of error, which doesn't involve the approximation, but this does. We have sine theta is now just theta, and n sine phi is now just n phi. Thus, we can express phi as theta over n. Now, let's go back to our picture. We need one more thing. The length, this length L for the beam within the glass will be useful to us. We'd have to apply a little bit of trig. So what we can do is we can express that length L as the thickness of the glass over cosine phi, just using some trigonometry with that right triangle. And applying the small angle approximation to cosine phi, we can get just t. Now, to find the distance between the rays, we can do a bit of more trig. We can express d as L sine of theta minus phi, which would be this angle right here, theta minus phi. And once again, we can apply the small angle approximation to express both of these as t theta minus phi, or simply t theta minus theta over n by replacing phi with theta over n. And finally, we get the result that we were looking for, t theta n minus 1 over n. So this is a tricky problem. It involves, we have to have a really detailed picture. We have to do some trig. We also have to apply some tricky small angle approximations. The giveaway is when they mention that theta is small. That really is a hint that we are going to be doing some kind of approximation there. And so that's it. Snell's law, some trig, and a small angle approximation. And that's the answer.